Okay, this is the second video in the series on the Prentice Hall Geometry Worksheet G85 Practice Law of Sines. In the other video that I did a few days ago, I mainly focused on these problems on the front side of the sheet. We had some problems where we had to draw the triangles, and then we had some problems where they gave us the triangles and we had to solve for the opposite sides. One thing, sometimes you have to do triangle sums to figure out what this top angle is because you need the angle opposite it. That's pretty much what's going on with those. Today we're going to focus on the second side of the sheet, which are more of the word problems, and also let's talk for a second about the actual law of sines. Using this as a reference triangle, vertex capital letter, opposite side small letter. It's true for every triangle that the ratio of the sine of the angle over its opposite side is the same for every side and angle pair in the triangle. I like to use this version, which is the angle in the numerator. A lot of books will use the version with the angle in the denominator. They really are all the same. And so basically what you're doing is finding three parts out of these ratios out of the four, like when you're doing a pair of these, and you're looking for the missing one, and so you cross multiply and then isolate the variable on the side and then solve. So let's look at these problems on page 2 here. So let's look at number 15. Now number 15, they give us the picture. It says a hot air balloon is observed from 2 points. So this at angle A, they're seeing the balloon up at 65 degrees. 800 feet away at angle B, they see the balloon at 37 degrees, and they want us to find the distance from point A to the balloon. So that's basically the side that they want us to find for this one. And then the answer needs to be rounded to the nearest foot. So using this triangle, I can see that this is opposite the 37, but I need to have another angle inside. They're giving me this side here, so I need to actually get this angle. To use triangle sums, I have to know what this angle is inside. We have an exterior angle theorem from geometry that tells us that the sum of these two angles is equal to the exterior angle. So if I did 65 take away 37, I'm going to get 28 degrees. If for some reason you don't remember the exterior angle theorem, which is kind of like a shortcut, you can do the supplement to this angle, which is going to be 115 degrees, 115 degrees, and 115 and 37 subtracted from 180 is also going to give us 28. So that would be the way to do it using the triangle sums. But we need to have angles inside the triangle. So with what we're given, we've got an angle and its opposite side. So we can say that the sine of 28 over 800 is equal to the sine of 37 over little b. When we cross multiply and simplify, b is going to be 800 sine 37 over sine 28. And so we bring our calculator out and we're going to punch those numbers in. So 800 times 37 sine equals, divided by 28 sine equals 1025.519. Round our answer to the nearest foot. We're going to round off to 1026. So the length of B is 1025.5, but the answer that they're looking for is rounded off to the nearest foot, 1,026 feet. 1,026 feet. Almost 2 miles. Okay, let's look at number 17. For 17, a plane is flying between two airports that are 37 miles apart, or 35 miles apart. The radar in one airport gives a 27-degree angle of elevation to the plane, and the other airport registers a 69-degree angle. Now, we want to use the law of sines on this. They want us to find how far is the airplane from each airport. So we need to find how far the airplane is along, if we call this ABC. How long is, we need to find B for that triangle, and also we need to find small lowercase a for that triangle. And they're giving us enough information with these two angles and triangle sums to figure out what angle C is. So if I add 27 and 69, I get 96. I need to get the difference of that in 180. It comes out to be 84. So angle C is 84 degrees. So we're going to use the law of sines. We've got 84 with 35. We've got 27 degrees with lowercase a, and we have 69 degrees with lowercase b. So this is going to be two applications of the law of sines. I'll go ahead and set both of them up, and then we'll just work them all at one time. So for the, say for side A, we've got sine 84 over 35 equals sine of 27 over lowercase a. When we cross multiply and simplify, a is going to be 35 sine 27 over sine 84. Okay, you want to do the same thing for b. Sine 84 over 35 is equal to sine 69 over b. B is going to be 34 sine 69 over sine 84. Okay, so over here, A is going to be equal, B is equal. When we get our final answer, the answer needs to be to the nearest tenth of a mile. Okay, so to do A, we've got 35 times sine 27 sine equals divided by sine 84 sine equals 15.97. They want this to the nearest tenth, so this would actually round up to 16.0 miles. And I'm going to leave it as a 0.0 because this 0 shows that there was some rounding that went on and that it wasn't exactly 16. Okay, to do B, we've got 34 sine 69, 34 times 69 sine equals divided by sine 84 sine equals 31.916, so 31.9 miles. So given these angles, that's these are the distances from the airport. Okay, let's look at, say, number 20. Now for these, they're giving us a situation. We need to draw the triangle and represent the situation. And the other information that we're given is that in each one of these triangles, there's 4 problems. We need 4 triangles for those. They're giving us some of the angle measures. So for 20, I want to sketch a triangle. I'll call it ABC. Angle A is 25, and angle B is 50. So angle A is 25, angle B is 50. So 25 and 50 added together make 75. 75 from 180 leaves 105. So those are the angle measures that we have. Notice that the triangle doesn't have to be to scale. You just want to be able to represent the data like a graphic organizer. Now they're telling us that AB, which is actually the little C side, is 53.7. And they want us to find AC, which is actually the little B side here. So we've got an angle and its opposite side, the 105 with the 53.7, and we need to find B, which is opposite the 50. And we had to use triangle sums to actually calculate that 50. So I want to set the ratios up. Sine of 105 over 53.7 is equal to sine of 50 over B, which is AC. Okay, so we want to finish this up. Cross multiply and simplify. We're going to have AC, which is the little B side, is equal to 53.7 times sine of 50 divided by sine of 105. Okay, bring the calculator out. 53.7 times sine of 50, 50 sine equals, divided by sine 105, 105 sine equals, we get 42.58. They want the answer to the nearest tenth, so 42.6. And does it give us units? It doesn't give us any units, so 42.6. These others are pretty much the same as those. For each one of those, I would imagine that you would need to draw a new triangle for each one. It doesn't have to be to scale. Label the given information in the triangle, and then use what information they give you for the problem, and basically end up seeing which ratios you need to set up. Let's look at 22 here. Suppose you know the measures of two sides of a triangle and the measure of the angle between the two sides. Okay, so let's draw a couple of triangles. Let's draw a right triangle. And let's draw, it looks equilateral, but let's not call it equilateral, and let's draw an obtuse triangle. So we'll try like 3 different triangle cases here and see if we can find an anomaly or whatever. If you know the measures of two sides and the measure the angle between the two sides, can you use the law of sines? So let's say we know that this is a 12 and this is a 10, and that this angle is 100. For here, okay, we got a right angle. Let's say we know that this is a 10, this is a 12, and this is a 20. And for this one, let's see, let's have it be acute. Let's say that this is a 40, and that this is a 12, and that this is a 15. Okay, so I just threw some random numbers in there. So let's kind of look at these. Can you use the law of sines to find the remaining side and angle measures? Now, okay, so we have a area formula that we could use to calculate the area of this triangle, which is 1/2 the two sides multiplied together times the sine of the hinge angle, or the included angle between. But we don't have a situation where we can actually find out what this side is, at least not at this point. This is actually maybe a law of cosines problem that we'll be coming up on a little bit later on in the book. So at this point, I don't see a way, not knowing the law of cosines, that we can actually do that. Here we could, okay, we know that this is with a right triangle now, knowing that this is a 20, we could actually know that this has got to be a 70, which gives us enough information to solve that triangle. So with a right triangle, it seems as though we would have enough information, because actually the 90 is being given to us. That brings to mind another triangle like this. Let's say we know that this is a 90, and that this is a 12, and that this is a 10. Let's see, do we have enough to be able to find this side here? We know that this is a 90. We could do Pythagorean theorem, figure out what the hypotenuse is. We've got the hypotenuse opposite the 90-degree angle, and that lets us find out what the other angle is. So it would also work for a right triangle with that situation. With an acute triangle, knowing that this angle, now not saying that this is isosceles or equilateral, there's not really, without the law of cosines, a way of figuring out what this opposite side is. So we can't actually know what any of these other angles are either, just given the one angle. So it seems as though we can't say that it works for other than right triangles. Okay. So if you have any other questions on any of the other problems on this page, let me know, and I'll either put a video together or see what questions you might have.